Okay, here's something, to be completely honest, we did not cover at all this year. We just ran out of time. It's not very difficult. What we're going to cover right now are what we call nuclear reactions. They're very simple. In a nuclear reaction, instead of a chemical reaction, the nucleus is changing. In a chemical reaction, the electrons are changing, and we should know they're on the outside of the nucleus. All right? In a nuclear reaction, we lose a subatomic particle, generally an alpha, beta, or a gamma particle. And we're just going to talk about alpha right now, because I don't remember beta being something that is usually tested. All right, so when an alpha particle is released, we call it alpha decay. So this is the nuclear reaction for alpha decay. And what I have here is a large atom, and this only happens with really heavy atoms. Up here's the mass, and I got that just from the periodic table. Seaborgium is the name of this, and it's element number 106. That's the number of protons. Okay, so one more time, a nuclear reaction. The nucleus is actually losing a little bit of matter and giving off some energy. So what we have seaborgium going through alpha decay to become rutherfordium. That's not supposed to be capitalized, but whatever. All right, so here we go. An alpha particle, this little alpha particle, it's made out of 2 protons and 2 neutrons. So its mass is actually 4. All right, and if we were to give it an atomic number, we'd say its atomic number is 2, because protons determine the atomic number. Hopefully you're somewhat okay with that. Now, if you think about an element that has a mass of 4 and an atomic number of 2, that element would be helium. So oftentimes, an alpha particle is written as He42. Now, it's not a helium atom because it doesn't have the electrons, so it's technically referred to as a helium nuclei. So here we go. When seaborgium goes through alpha decay, it releases an alpha particle, or a helium nuclei, and whatever's left over. So here's how we figure out what's left over. In these reactions, you take the mass, and then you go over. You have 4 plus some number that will equal whatever that mass number was. Because the law of conservation of matter works in nuclear reactions too, I have to have the same amount of stuff on the right as I did the left, and I can't change coefficients here. So if I lost 4, then my mass went from 266 to 262. If I lost 2 protons, then my atomic number went from 106 to 104. And then all I would do is look on my periodic table to find element 104, and that would be Rf. Okay? In a nuclear reaction, an alpha particle is ejected, He42. We just subtract 4 from the original mass, right here, to get our new mass, and then we subtract 2 from the protons, which is 106, so that becomes 104, and just find it on the periodic table. Let's work through a quick example. So let's do the same thing now. I'm going to leave that all the same, but we're going to say that uranium, and on the periodic table it's 238 and 92. So I have 238 and 92. If you're really studying, pause and see if you can figure out what it goes to. If you're just doing this to pass time because I told you should, then just pay attention to the answer, I guess. Okay, so uranium goes through alpha decay, giving off an alpha particle plus whatever I have left. It was 238. I've lost 4, so it must become 234. It was 92. It's lost 2, so it must be 90. And then I just look on the periodic table for what 90 is, and that's thorium, or TH. Okay, the key to these is they have to have balance. They'll usually on the core test have you fill in one of these numbers or determine what the actual element is that's there. In a beta decay, it's a little bit different. Small atoms go through beta decay and they actually go up one. So we could have nitrogen turn into oxygen. It's a little bit trickier and it's not going to be tested, so we're not going to worry about it as much.